Hi, so in this video we're going to cover problem 42 from the section on parametric surfaces and their areas. So problem 42 says find the surface area of z equals the square root of x squared plus y squared between y equals x and y equals x squared. Okay, so there's two things you need to do in this problem. One is you need to set up a parameterization, and the second is you need to integrate over your particular domain. So we have to actually use this information here to find the domain. So recall that the area of your surface S is the integral over your domain and you take the cross product of your function that points at a particular location. This is your position function, R. It tells you go here, right? It just gives you the position. This is our formula, but what is a parameterization that works? What about the obvious one? The obvious parameterization is Rxy equals xy fxy, right? We discussed this in the previous video. This is very obvious, right? So you have 2 points on the domain, and this third point, which is the range. And when you sort of combine the domain with the range, and you think of it as a single object existing in three-dimensional space, then you can do that sort of parameterization. Now, perhaps throughout the whole course, this is how you've already thought about the three-dimensional functions. But again, they're not actually three-dimensional. The functions that we've been dealing with in this course have, for the most part, been two-dimensional. What do I mean by that? I mean, the inputs are two-dimensional. This is no different than in Cal 1 or Cal 2, when you plot a function over the real line. You have to use 2 dimensions to do that because the output adds a dimension, and that is the value f of x equals y. In any case, we're going to view this as a three-dimensional object, and that's our parameterization. It's given right here. Now, there is a formula that you can use to compute this surface area when you have this sort of parameterization. Let me tell you, do not memorize that. It's more work. You can mix it up with something else. It's best to just not do that. Instead, derive it. It takes no work at all. So what is my u and my v here? Well, it's x and y. So I'm going to replace that with x and y. So x and y. And now the question is, well, what is Rx and Ry? Well, this is very straightforward, right? 1, 0, and the partial derivative of f with respect to x, right? So the derivative of x with respect to x, that's obviously 1, and the derivative of y with respect to x, that's obviously 0, and with respect to x, the derivative of f with respect to x is fx. So likewise, when I do this with respect to y, I get this. Okay, so using this information, I'm going to compute the cross product, because I need that right there, and go from there, right? Okay, so ijk 1, 0, fx, 0, 1, fy. Okay, so when I multiply those two, they cancel, so I get minus fx minus fy and 1. Well, we need to find the absolute value of it, so I'm going to take the norm on this whole thing, and in the end, I should get this. Okay, so this ultimately means we can rewrite this up here as the square root of fx plus fy plus 1 dA. And this is the formula that you'll see out of your book. It is on page 1158. But again, I don't advise you to do this. They don't use f, they use z. And again, this is just another way to jumble things up. Keep things simple. It only took me a moment to calculate. And I'm also talking and looking at my computer camera and all that. It's not how you would do it on your own. You'd go much quicker. Okay, so what is this domain D? Well, let's draw our functions. So this is, let's say this is y equals x, and this is, let's say, y equals x squared. Where do they meet? Well, they meet at 1, 1 and 0, 0. So really what we want to do is we want to integrate either this way or this way. Remember, ultimately, we're going to set up a box, and outside of our strip right there, the function that we're going to integrate is going to equal 0. But we don't want to get hung up on fundamentals too much. So I'm going to integrate in this direction so that my outer integration is going to be with respect to x. That's going to be from 0 to 1. Okay, so this means that my outside integral is from 0 to 1. My inside integral is from x squared to x. And I'm going to erase this now to give me some space. What is f? Well, f, x, y, that's just z. And f with the derivative of f with respect to x, that's going to be this right here. So that derivative it's that. Okay? Now I'm going to square it so that square root in the bottom will go away. Okay, so square it and the square root goes away. So I should get x squared plus y squared. And then I'm going to do that again. As you can see by the symmetry, I'll just pick up a y up top. So I get this. Now I have this 1. What is 1? 1 is just anything divided by that same thing, right? So I'm going to go ahead and write this as x squared plus y squared over x squared plus y squared. dy dx, right? Because we're first going up and down. Okay, so cleaning things up, I go from 0 to 1, x squared to x, and x squared plus y squared plus 1. Sorry, that is not correct. X squared and x squared, I get 2 x squared plus y squared. Well, that turned out to be really nice, right? Because effectively, I can just cancel all of that out, and then don't forget your dy dx. So all of this simplifies down to 0 to 1, x squared to x, and I have this square root of 2, I can just pull that outside. So let's do that. Square root of 2, and then dy dx. And the rest is pretty easy, so I'm going to leave that to you and keep this video short. It's at 11 minutes, and I'll see you in the next video.